So today, welcome. We'll be starting regarding the buck converters. So, as you can see in the chopper configuration, we are having a step down configuration over here. You just look, this is called the step down configuration. Okay, so step down chopper. In this case, your alpha is the duty ratio, which is nothing but your T on time divided by the total time. The total time would be your T on time plus T off time. This would be your total time of the chopper when it is functional. Now the switch over here, okay, resembles your chopper. This chopper can be made up of GTO MOSFET, but in DC-DC converters, widely used chopper driver circuit is designed from the MOSFET that you should keep in mind. Now here there is a freewheeling diode. Okay, let's concentrate on this buck converter. How does it operate? Now there is two modes of operation. One is the thing is that when your this diode freewheeling diode is reverse biased, okay, in that case means if the current is moving like this direction, okay, so in diode, if your current, this is your P and this is your N, the current is flowing reverse, that means your tail positive wala part is getting connected to N and this arrow to this, then it is reverse bias. Now here you see positive wala part is getting connected to N and this arrow to P. So this is reverse bias, which is resembled by an open circuit. So in this only this part, so that means this diode will open up. Only this part of the circuit will be remaining. Only this part of the circuit will be remaining. Which part? That I've drawn in the next section. I'll just show you because I wanted to save the time. Where I've drawn it? Yeah. Okay, I've not drawn it. Yeah, not drawn. I'm sorry. Okay, no issue. So that means only this part of the circuit will be remaining for this. So this is your Vs and let this be your chopper. Okay, so diode gone. We're left with VL and this VC wala part and the load wala part. Clearly your VC is equal to V naught, correct? Because it's connected in parallel, right? And this is your Vs. So if your chopper circuitry, so now your connection is like this, right? So your Vs in between VL is there, right? And inductor is there. So Vs would be equal to VL plus V naught. If you apply the KVL to the outer loop, so Vs will be equal to VL plus V naught. Or else you can write VL is equal to Vs minus V naught. And VL can be expressed as L di by dt, Vs minus V naught. Take di by dt this side, Vs minus V naught. L you bring down, take dt on this side, then integrate. Okay, integrate on both the sides. This you will integrate from the minimum value of the change in current, right? That is delta IL. That is nothing but I max minus I minimum, which would be represented by delta L. And here, this is a constant value, it comes out of the integration. So this would be equal to this. Okay, delta IL is equal to Vs minus V naught by L by T on. Now you notice that I told you already, Vs output, okay, Vs is the output voltage and sorry, V naught is the output voltage and Vs is the input voltage. Okay, so Vs by V naught, that is output voltage by input voltage is your duty ratio. Also, you noticed here that, okay, here T divided by, see, T on divided by T is your alpha. So that means T on can be represented as alpha into T. The same thing I've done. And 1 by F is equal to T. So T I can represent in terms of 1 by F. So this T on, how I have written? I have written this T on in terms of alpha by F. Same thing. So alpha by F I'm representing and Vs minus V naught, right? So again, I told you Vs by V naught is equal to alpha. So Vs can be written as alpha V naught. So I'm just substituting back here and I'm just taking this Vs outside. So once I take this Vs outside, I'm left with 1 minus alpha into alpha by F into L. So this is my delta IL. Okay. So this would be my equation for delta IL is equal to Vs 1 minus alpha by FL. This is for the buck converter. So this is the equation alpha 1 minus alpha FL. At duty ratio alpha. So in some books, this is written as D, which is the one and the same thing. D or alpha is the same. Now, alpha delta IL max, if it is zero point 0.5, so this is 1 by 2. 1 minus zero point 0.5 is again 0.5, 1 by 2. So it would be Vs by 4FL. Now, when the chopper is in off mode, okay, and the freewheeling diode is on. So if you go back to the circuit, Okay, chopper is in off mode. So this part of the circuit is getting disconnected. Only the remaining part of the circuit is from the freewheeling diode. So you are having this VL, you are having this capacitor, and you are having the load outside it. So you are having VL, VC and V naught. And you know that VC is equal to V naught. So in short, if you have to write the KVL, so VL plus V naught would be equal to 0. Algebraic sum of the voltages at a network is equal to 0. So the same thing I'll be writing over there when it is in the off mode. So what I write, okay, where we went, okay, here we are. So that means in the off mode, VL plus V naught is equal to 0 or VL is equal to minus V naught. And now V naught again from the same V naught by Vs is alpha. Same thing I'm doing. Alpha is equal to T on by T, right? And 1 by T is F. So F into alpha is equal to F into T on. So delta VC value is written as, see, I need to get to this value. How do I get to this value? You do it from the charge equation. So Q is equal to C into V. Okay. I differentiate. This del value means differentiation, d by dt. So I differentiate the charge, differentiate. See, capacitor is a fixed quantity, this is a number, and inductor, so it's constant, it comes out of the differentiation. Remaining voltage is variable quantity, it remains. So delta VC is equal to delta Q by C. Now, delta Q by C here in this chopper arrangement would be given by the area of the triangle. Half, okay, into base into the height, which I'll be showing you. So that would be equal to delta I by T8, and T is given as 1 by F. So this comes as delta I by 8F charge. Now VC is nothing but delta VC is delta Q by C. So it is delta I 8FC. So that is your delta VC is equal to delta I 8FC. Okay. So now here you just notice here what happens. So this is your first portion when your T on is there, right? So the period is moving from 0, right, to T on, okay, and up to T, right? So the total period T on plus T off is your T period, right? So T off is the period, that is T minus T on, okay? So if it is off period, and then this is the freewheeling diode off period, so in that on period, your VL is Vs minus V naught. In the off period, your value of Vs, right? You just saw that VL plus V naught is equal to 0. So VL was equal to minus V naught for the off period, right? When it was off. Okay. So your charge was storing, right? The inductor, the capacitor was there, right? In this circuit. So it was storing, and this is releasing, okay, in the on period. So this is the triangle that you are forming. Okay. So this triangle ka half base into height, that is half into T by 2, and the average of the current del I by 2. That's what I got, Q, right? So del I was equal to 8FC, and I again substitute back this del I value which I previously calculated, del I value as alpha 1 minus alpha Vs by FL. So once I put this value del I here and 8FC, I get a value delta Vc is equal to alpha 1 minus alpha Vs 8F square LC. Okay. Now that means if we increase the value of what here frequency, what is going to happen? Voltage is going to decrease. Okay. So now one more important fact here is that, so in the buck converter, if you need to calculate the critical inductance will happen when your I naught output voltage would be equal to delta IL by 2. What would be your output voltage? Hmm? Output voltage would be equal to V naught by R, right? I naught would be equal to V naught by R, right? I naught. But what is your V naught? V naught is nothing but alpha Vs. Same thing I put over there, alpha Vs by R. And delta IL, that alpha 1 minus alpha Vs divided by FLC, right? This is your, this thing into 2. So keep this alpha here, cancel out. LC would be equal to, this is an important result that you need to remember for gate examination. So gate important result, okay? And similarly, critical capacitance V naught would be equal to delta VC by 2, like half of it. So just put the value of delta VC, that is your, see, delta VC from the previous equation that was equal to this thing, delta IL. So you just substitute alpha 1 minus alpha Vs by FL, and here one F is there, so it becomes F square LC. So this del, if you do 2, then it will become 16. So your V naught will become equal to alpha 1 minus alpha Vs 16 F square Lc. And V naught you can write as alpha. So alpha alpha cancels. Vs cancels, right? So bring this capacitance here. And now you are left with 1 minus alpha. This is another important result. Okay. Filter capacitance result. This comes for the buck converter. Okay. Buck converter. Now in the similar grounds, okay, we will be studying the boost converter and then I'll show you certain problems associated with the grid. So the boundary condition, this is for the boost converter, okay. So you noticed now let boundary condition means the maximum value of this I max value will be equal to your I naught plus delta I, and the minimum value is your I naught minus delta IL by 2. Now in the boost converter, if you are seeing here, you see in the buck converter, what did we see? The arrangement of the chopper, right? In the buck converter, if you go back to the previous slides, did you notice in the buck converter? Here the chopper is in parallel, right? This is my chopper. There in the arrangement, there the chopper for the buck converter was where it was in series, right? Buck converter, if you just look here, your chopper first came in, right? And then was your diode, and then was your inductor and capacitor and your load resistor, right? Load resistor. So this was your diode, this was your inductor, L, capacitor, and so C R and C are parallel here, L, diode, this is in. Now here you notice L to is always in series, D and this nothing changes. Only the chopper arrangement comes after the inductor. Here it comes prior to the inductor. So it will give you a buck arrangement. Now notice here what happens in the boost converter. This boost converter produces higher output voltage than the input voltage. That means V naught would be significantly greater than Vs. If V naught is the output voltage, Vs is the input voltage. Now, the chopper is off or switch off. Okay, when the chopper would be off, like here, if you switch off the chopper, okay, disconnect it, then your circuit is this, right? This is your circuit. So this is the circuit. So the current is flowing through the diode. Now, when the current is flowing through the diode, this plus and this minus, that means you take the tail as plus is connected to P and this to minus. So it's a forward bias, which is replaced by a short circuit. So this is your circuit here. So this circuit clearly indicates again Vs would be equal to VL plus V naught, right? Because the voltage across R and voltage here are the same. Okay. Now, if you notice here in the off mode, okay, when the chopper is your, for example, on, okay, when you connect the chopper there, when the circuit becomes goes like this, okay, now here if the current is flowing like, okay, so what is going to happen? Hmm? So now this is the current flow like this, it is flowing in the reverse direction. So across the diode also, if you notice, okay, now the flow of the current is with the blue color I had drawn it, so it is moving like this, okay. So the direction of the current flow is through. So this is your arrangement, okay. So the total arrangement for this would be it is moving like this, okay, and then your this diode is becoming reverse biased, and this is your current direction of I naught is going like this, okay. You notice here I naught will move upwards, and IL is moving, IL is reverse, IL is this, and I naught is this, okay. So that means IL is equal to minus I naught. Now the condition IL is equal to minus I naught, that means L di by dt, if it is equal to the input would be, see here from this it is clearly noticed, right? So here VL is there, right? All in this, if you apply KVL, VS, okay, is equal to VL. So here if you apply, so this would be minus VS plus VL is equal to 0. So this is VS is equal to VL. So L di by dt would be equal to VS. So that means if you just integrate this from minimum to maximum value, we'll get an equation. This will be delta I and this will be T on. So delta I would be equal to, okay, Vs by L, which I have written, okay, and this would be T on. And you notice that T on can be replaced by alpha F, which I have done previously also. Just refer back previously, okay. Now, see, this is your chopper circuitry. When the chopper is in off mode, your circuit is made like this, so which I was already discussing. But notice here your Vs value, okay, output here is always greater. Yeah, V naught is always greater than Vs, right? So that means this result would be always negative. If you are supplying subtracting Vs minus V naught, the result would be negative. So therefore, the VL value will be equal to minus Vs minus V naught. Okay, now if you are equating in the on and the off position, in the on position, the voltage you are having Vs into T on, and in the off position, like for balance of power, right? There's a law of conservation of energy. Whatever can be stored, that would be discharged, minimizing the losses, conduction losses, and all, which are very narrow there. So if we equate these equations, okay, so this is the value. So I took this value, right? I wrote ultana because your VL is minus of minus V naught minus Vs. That's why I wrote V naught minus Vs into T off. And I'll just substitute these equations back. So here you see Vs and T on is there, and T off is there. So I just take this Vs and T off here. So T on plus T off will become T. So I have Vs by T is equal to V naught by T off. Again, what do I know? Vs by V naught is how much? Vs, if it is input output, so it will become 1 by alpha. And T can be written as F, 1 by alpha F, right? So V gone. This is equal to T off. T off is equal to 1 by alpha F. So let me just go to the next slide. So we notice that T off is equal to 1 by alpha F, right? So here what you do is you just write Vs by T and V naught here, okay? And T off you can directly write as 1 by alpha F. That is one easy way to do. So if you do Vs by T here and V naught, or it is better to do like this. Okay, this T off, see, T on plus T off is equal to T, right? So your T off value would be equal to T minus T on, correct? T minus T on. So now just substitute back T minus T on here, Vs by T is there. Divide this both sides of the equation by T. T cancels here also. T cancels. So 1 minus T on by T, right? T on by T. That is alpha. So 1 minus alpha by Vs by V naught. So your V naught value will come as Vs 1 minus alpha. Same you do for the power equation, equate the power on the output and the input side. Same way V naught by Vs, which is already you got V naught by Vs as 1 minus alpha. Is by I naught is equal to C. Is is equal to I naught 1 minus alpha. Okay. Now for the charge, the same thing you do C dVc. And in this case, the charge would be equal to, okay, I into T, right? So I naught into T or T naught. So this is divided by C. Okay. So again, your this thing T on is equal to alpha T or alpha by F, right? So T on you replace here by alpha by F value. So that is I naught by C. Okay. So delta Vc would be equal to alpha I naught Fc. I naught would be equal to V naught by R, which is nothing but V naught by Vs you saw. V naught is equal to what? V naught is equal to Vs 1 minus alpha, right? We saw na. And in this case, boost converter case. So this would be equal to this. Now critical value will appear at when I naught is equal to delta half IL by 2. So the critical value will appear. You just substitute the value of this, right? I naught value you already knew. V naught by R, that is Vs 1 minus alpha by R. And this will happen at delta IL by 2. So delta IL value you have just seen, right? Delta IL value we just calculated here. Where was the value? From the previous pass equation, yeah. So is was equal to uh, so that is minus of that, right? So your I delta IL value we have, just a second. So yeah, delta IL, okay, okay, okay. Delta IL is this value. Delta IL is equal to alpha Vs by FL, which we had done previously in the previous case. If you just go back to where I started. So anyways, if you just scroll back there, you will get here. Okay, delta IL is equal to, so just substitute back this equation down there. Okay, and you'll get the answer for that. Okay, so I naught is equal to delta IL by 2. Just substitute here for the critical value of the inductance which happens at this. So this is Vs cancels. Okay, then your L you have to take this side, L you took this side, 2f remains there, alpha is there, and then 1 minus alpha comes on top, R comes on top. So this is the value. Alpha 1 minus alpha R into 2f. Okay. So see, now you notice here in the on period, what was your VL equal to VS, right? In the off period, it was the negative value of it. Your voltage, this VL is what? Voltage through the inductor, right? IC is the current through the capacitor, and these Imax is the maximum current. So this is the charging period. This is the discharging period. That's what is happening in this case. Now let's take some problems. Okay. Similarly, critical value of this will V naught will happen at delta VC by 2. Just substitute back these values of VC from the previous. The important thing is that you need to remember these results. You have to remember these results. In the gate examination, you can't derive. And the problem with me is it's very difficult to remember. Okay, now the gate type of question is the figure shows a chopper is okay. Okay, this is a simple question over here. Okay, let me just read the question properly. Uh, okay, let's go here. Okay, okay, this one also we will do. Let me first do this. See, in the DC-DC converter shown in the figure, the current through the inductor is continuous. The switching frequency is 500 hertz. The voltage V naught across the load is assumed to be constant and ripple free. The peak inductor current in the ampere changes to. Now the peak inductor current Imax would be equal to IL plus delta IL by 2. If they ask the minimum current, I minimum, so whatever the value of IL minus delta IL by 2 you will get. Now here you need to calculate what? Delta IL and IL. So in order to calculate the IL value from the boost converter, you know that your IL value is nothing but IL would be equal to I naught 1 minus alpha straight away, right? Because see, if but in order to go there, right, you need to convert that value. Now you need I naught value, right, in order to get there. So first you have to calculate the V naught value. Then R is given in the question. R is equal to 10 ohms. It is given in the question. V naught is given in the question 40 volts, right? L is given as 2 millihenry, and the input voltage, that is your Vs, is given as 20 volts. So you start with this, you need to calculate V naught. So in the boost converter, the equation is simple, V naught. So the equation that you require is V naught is equal to Vs 1 minus alpha. So V naught is 40 divided by 20, and alpha is given there, right? In the question, it's given there. What is the duty ratio? Frequency and the voltage V naught the capacitor is okay. No, duty ratio you need to first okay, you have to calculate here. You will get the duty ratio from here. V naught and Vs is given, right? So this is your 1 by alpha. So what you do is that you just reverse it, right? So this is 40 is equal to 20 divided by 1 minus alpha. 20 ones are 22s are. So you do this 1 by 2, it will become 1 minus alpha. 1 goes this side, so 1 minus alpha will become alpha is equal to zero point 0.5. So first thing is this, alpha you calculated zero point 0.5. Then you need the value of I naught. So I naught is V naught by R straight away. So that is 40 by 10. This is 4 amperes, right? And then you need the IL value, right? IL is nothing but we saw the equation IL is equal to I naught 1 minus alpha. Okay, so I naught is your 4, 1 minus zero point 0.5. This will become 8, correct? 4 divided by 1 minus half, 4 by half, which will become 8 amperes. Then you have alpha Vs by FL, correct? Alpha value you got zero point 0.5, Vs is 20, F value is given in the question 500 hertz. Substitute that value, L value is also given 2 millihenry, 2 into 10 power minus 3. From there you will get delta IL value. Okay, if you just calculate these values, so IL value what as 8 amperes, okay, and this value if you just calculate, this will come as 10, right? Right now this will come as 10. So then delta IL is equal to 10. So this is IL plus delta IL by 2. That is 8 plus 10 by 2. This is 13 amperes. Okay. This has recently appeared in the gate examination. This next question we'll be doing because I don't want to make big these things. So I'll just stop my recording. Okay.